In the last lecture, we have seen about the basic of modulation scheme. We had defined the intersymbol interference and how we can get rid of the ISI. So, intersymbol interference, uh, because of problem of band limited channel or system, we are observing the ISI. So, when we want to reduce the ISI, we need to use a means the signal also, input signal also should be band limited, so that we will not experience the too much difference in the output and ISI, significant ISI. So, the problem of ISI can be solved by using a pulse shaping signal. So, we have seen in the last class that if you use a sinc function, means your time domain function, time domain signal is a sinc function, and if you try to use, you can achieve the 0 ISI. Now, the method of getting the 0 ISI is by using the sinc function, is called as a Nyquist signaling. There are various pulse shaping method we can use. The common pulse shaping method, which is widely used in digital modulation, that is a raise cosine filter. So, raise cosine filter is applied after the modulation, and this is the behavior of the raise cosine. In time domain it will look something like this, and in frequency domain it will be like this. So, the in time domain we can write in terms of sinc sin pi t by Ts by pi t by Ts, and it has a cos function. So, for various value of alpha, here alpha is nothing but a roll factor, you will have a difference in terms of the bandwidth. So, alpha is equal to 0, the pulse reduces to sinc. So, when we make alpha is equal to 0, this will be cancelled out and you have a sinc function. So, you will have a 0 ISI, and alpha is equal to 1, the spectrum becomes relatively wide. So, there is a little wider spectrum. So, we try to ideal value of alpha is 0, but in practical scenario it is not possible to use alpha is equal to 0. So, we try to typically use alpha in between 0.3 to 0.5. We will not use more than 0.5. If we try to use the more than 0.5, then your signal will have a wider bandwidth and it will have a ISI. It will observe the ISI. So, we need to use a pulse shaping in order to reduce the ISI, and it is widely used in a digital communication. And this is a raise cosine function can be applied to your bit stream, and you can make a pulse shaped bit stream. Another important feature that you should know for digital modulation is the signal constellation. So, how signal constellation will look like? So, in signal constellation allows us to visualize the modulation schemes, and more importantly the effect of non idealities on them. So, let us say if we have a PSK modulation as PSK, which is a function of Bn cos omega ct, where Bn can be either plus or minus. So, this is a Bn sequence. I have a positive data, means which has a multiple data points with plus 1 amplitude, and multiple data points with the 0 amplitude. So, this plus and 0, now if we try to see the in ideal function. So, this is a ideal, there will be not any distortion in the amplitude, and your signal will exactly look like a signal that we have seen in the PSK. But in reality, when it will pass through the channel, noise will be added, and that noise is converted to the if you try to make a constellation diagram of the same, when you try to receive a 0 or 1 amplitude. So, the amplitude for this will be different, for the another bit stream will be different. So, when you try to put on a single line, in this case when we have kept in a single line, it was just look like a dot, but there is a possibility there are multiple bits are there at the same point with a same amplitude. But when we try to pass this signal to the channel, which is a noisy channel, and it will add a noise in that, the amplitude of the signal when we try to reconstruct will have a different amplitude, and it will uh, be at different 0 or 1 amplitude, but it will be near around that. So, when we try to detect the signal 0 or 1, we need to put one threshold line in between, and this threshold line will tell us that which side of the bits are 1 and which side of the bit are 0. So, here this signal constellation has only one axis, because there is a only we are changing only the one part of the carrier signal, that is a one phase. And by seeing the signal constellation, you can easily analyze that your bits are corrupted or it is a ideal. It is also we will see in QPSK QAM, it has a many application, and it is easy to understand the how the modulated signal are reconstructed. There is a FSK constellation. So, if the frequency is different, so in FSK receiver must decide whether the received frequency is omega 1. Let us say if B1 is equal to 1 and B2 is equal to 0, that means it is omega 1, and omega 2 when B1 is equal to 0, B2 is equal to 1, then we will consider a omega 2. So, this SPSK T, which is equal to B1 cos omega 1 T plus B2, here it is S FSK T, which is equal to B1 cos 1 omega 1 T plus B2 cos omega 2 T, where B1 B2 which is equal to 1 0 or 0 1. So, here if we see the PSK signals are less susceptible to noise than FSK signal, because their constellation points are farther from each other. So, here in the previous example, your PSK, we can put easily threshold over the PSK signal. However, when we try to make FSK signal, what FSK signal has a at one side, this is a B1 and B2, it has a omega 1 frequency and omega 2 frequency. So, this is a ideal that we have transferred, and if there is a noisy channel, then all your frequency means amplitude and frequency is different at this point, and here also there is a change in the frequency. So, when we try to put the threshold to detect the ones and 0, this is a decision boundary or decision threshold, it can be tell at us. We can not have a sufficient room for detection, and that is why PSK signals are less susceptible to noise than FSK signal, because their constellation points are farther from each other. So, this mostly the PSK are widely used compared to the FSK signaling. There is one more term related to constellation that we should be aware, that is called the error vector magnitude, EVM. And when you want to try to design a transmitter, or when you try to reconstruct the transmitted bit pattern, this EVM is very good measure of representing the deviation of the constellation points from their ideal position. So, if you if you know the error vector magnitude EVM, then you can easily get that how your constellation points are distorted, and this can easily be identified by using error vector magnitude term. So, the EVM, so how exactly it has find out. So, in reality we want our point to be here, which is reconstructed, but what is happening that when we received the signal and we try to reconstruct the bits, it has a different kind of constellation at different points. So, what we need to find out the distance or a difference, that is called a error. This is a what we want, and this is an error which is added. So we need to make a error, we need to find an error for each points, and that error is squared and divided by number of points, and again square root of that term is divided with V RMS voltage. So this is a one way of finding the EVM one. Another way of finding EVM is this is related to RMS voltage quantity, and this is related to power quantity. So E means this EJ square, that is the average of all this that we are trying to do divided by the power, average power that we see. Here we can also define the EVM is also defined as a RMS magnitude of this error vector normalized to the signal RMS voltage, and if we can also express EVM in decibels, what we do is we just make a 20 log of EVM1 or 10 log of EVM2. Because this is a power quantity, we have just used a 10 log. If this is a voltage quantity, we have used a 20 log EVM1. So in reality, this EVM, what is the ideal value? Can you think? It is a but obvious, we do not want any error at all. So this E1 to Ej should be 0. So in reality, we want the error vector magnitude should be 0, but in reality it is not possible. So there are some number or some percentage of error will be there. So this is a mostly used in when we use a digital modulation and we try to reconstruct the signal. Quadrature modulation. So the way we have seen the PSK modulation, now the part of the PSK, when we try to expand, there is a PSK. So PSK signal without pulse shaping, your bandwidth is greater than 2 by TB, but PSK signal with pulse shaping, the bandwidth is around 2 by TB. So how to reduce the bandwidth of quadrature modulation? So what we try to use is a quadrature modulation. So we will reduce the effective bandwidth and the generation of QPSK. So the first term, that is a quadrature phase shift keying, it can be written as a ST which has a B2M AC cos omega CT minus B2M plus 1 S sin omega CT. So what is happening? We are getting a binary signal baseband data. There is a serial to parallel converter. So this is a serial data which is coming at the input. So with a TB bandwidth which is a 2 by TB. Now what is happening? We are dividing. So the one pulse we are sending to A, other pulse we are sending to B. So we are widening. So this is A and B, we are dividing the signal, and this A we are multiplying with a cos omega CT, and then B we are multiplying with the sin omega CT, and again we are here subtracting the signal. Either subtraction or addition can be possible. So why it is called a quadrature modulation? Because here we are using a combination of cosine and sine function, and because of the combination of cosine and sine function, this is also called as a quadrature modulation. And the amplitude means the only difference that we have added, we have converted to the A and B stream, which is divided as a half, and then that is added again. So this is how the your signal will look like. And QPSK modulation has a halves the occupied bandwidth. So your occupied bandwidth is a half because you have spreaded the signal. Similarly, if we use a more complex modulation scheme, you can reduce the complexity. So this is a QPSK constellation diagram. So there is a in phase. So in the PSK, what we have done? We have only one x axis, and there is a 0 and 1 we have at one side there is a 0 and at another side there is a 1. Now in QPSK, because we have added a sine function as well, so which are 90 degree to each other, then the another point that the change in the sign constellation. So these are the sign constellation. So here that if we try to draw it differently, if it has a different amplitude, it will look something like this, where this data one is a I, means the combination of this I and Q. So this is a positive, so positive 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 I and positive Q will give the one constellation, then positive I and negative Q, negative. So this is a positive, I will just try to erase. So there is a this is a positive I and positive Q. Here positive I, negative Q, here negative Q, negative I and negative I and positive Q. So we can also denote this amplitude either in terms of +1, here it is considered +1 or -1, or if it has a different amplitude, means if amplitude in terms of amplitude also we can write it down. So here there is a in the quantity which is in phase and quadrature phase can be drawn. So here we assume the bits B to M and B to M plus 1 are pulses with height of plus or minus 1. So in this example it is a with plus or minus 1. So you can write ST, which is a combination of alpha 1 AC cos omega CT plus alpha 2 AC sin omega CT. So alpha 1, so as I told, this is nothing but the x axis will give the phase PSK signal, which is a cos omega CT multiplied with the cos omega CT, and another is a quadrature. So more generally the pulse appearing at A and B in this figure are called a quadrature baseband signal. It is also called as a quadrature baseband signal, and it is also denoted as I in phase or Q quadrature. So I is nothing but alpha 1 AC and Q is nothing but alpha 2 AC. So mostly this denotion is widely used, I and Q, for drawing the constellation. What are the drawback? We have already seen the QPSK. What is the drawback of QPSK system? So here there is a abrupt phase transition. What is happening when there is a signal and there is a change in the amplitude, suddenly the phase will change. So in this constellation there is a 4 point if we have drawn, then there are a possibility that this point is reaching to this point, and again this point is reaching to this point, or this point can reaching to this, means there is a transition from phase of these to 3 possible way. So there is a extensive phase change. So square baseband pulses. So here what is happening, there is a 180 degree phase change, there is a 90 degree phase difference, and again there is a 180 degree phase difference. So this signal, this is a square baseband pulses. Now if we try to pulse shape, as we already have seen that we need to use the pulse shaping, and if we try to pulse shape the signal, what will happen, this transition will be converted into this kind of wave. Again this 90 degree transition is converted like this. So when we try, as we have seen in the last class, our ultimate aim of modulation is how better we can reconstruct the signal. And here in this QPSK signaling, because of the very wide change in the phase, we can have a we cannot easily reconstruct it or recognize the exact change in the phase. Even this 180, there is a drastic change from 180, and that if we do the pulse shaping, we cannot able to reconstruct it. So, a variable envelope signal requires a linear power amplifier. This is also important line that is added, because here these signals are carrying the much more information in the amplitude also, and when there is an envelope which is changing continuously, we need a power amplifier which is a linear. Now linear power amplifier will consume a high power, and also the efficiency is less. So there is a trade off here, that the modulation scheme that we use and the requirement of linearity in power amplifier. So this trade off should be overcome by the power amplifier designer also, and at other side the baseband engineer will try to analyze the better modulation scheme to overcome this issue. So this is a drawback that we should keep in the mind. That is why GMSK or GFSK modulation type of modulation scheme are proposed and used in the current GSM standard. So where the constant envelope modulation, as I told, required a high power efficient signal, and then there is a FSK generation that we can easily do by using the VCO. If you just change the voltage of baseband voltage, you will get the FSK signal. Now in GMSK filter, what we are trying to do, as we have seen in the ISI, we are not transitioning the amplitude, means the sharp transition we are not doing. So first what we will try to do, we will use a Gaussian filter, that is also one kind of pulse shaping method, and that will make the amplitude look something like this. After this will be applied to the Gaussian filter, and this it is applied to voltage control oscillator. So there is no sharp transition in the change of the frequency, and you can easily reconstruct the signal. So GMSK is used in GSM cell phone, it is also used in a Bluetooth. So this modulation scheme has a wide use in a GMS, in the application of GSM and Bluetooth. So we have seen the QPSK, and the next is a QAM. So what are the modulation scheme up to now? We have seen ASK, we have seen PSK, we have seen FSK, then advanced version of PSK, QPSK. We also observed the constellation diagram for PSK, FSK and QPSK. Now there was a phase change that we have seen in QPSK. Now if we try to combination of ASK and PSK, so QAM is nothing but I will say the combination of ASK plus PSK. So what we are trying to do here, we will use the amplitude and phase both together to modulate the signal. So it will help us to reduce the bandwidth. So how we are doing here? So this is the in phase axis and quadrature axis. So the first point we will try to apply plus cos omega ct plus sin omega ct. So it will be something around this. This is the point that we try to send. Then what we will do is we make a plus cos omega ct minus sin omega ct. So there is a I which is a plus and another is a minus. So this is a plus and this is a minus. So this point we will try to send. Then there is a minus, so another is this constellation that we try to send. Then minus cos omega ct and plus sin omega ct. So, there is a minus cos omega ct, which is this at this 4 point. Again this 4 point we try to send, and then this 4 point. So, this 4 point has a amplitude of a +1. So, there is a +1 amplitude, and this can be written as a alpha 1 AC cos omega ct minus alpha 2 AC sin omega ct, where alpha 1 and alpha 2 can be plus or minus 1 plus or minus 2. So, in this case it is a 1 plus or minus 1, and we are getting for constellation. Now, if we try to do the I plus and I minus, so there are because there is a 4 variable, we will get a 16 combination, and there is a amplitude. So, you can see the amplitude is a change. This is sin omega ct with the same amplitude, and cos amplitude has been changed. Again the cos omega ct has a and sin omega ct has a different amplitude. So, this is an analog way of explaining the QAM, but in reality this QAM modulation has been done at the digital baseband side, and then it will be converted to the analog, or when we try to do the try to send the signal to the carrier. So, this entire processing, it is better to go back to the digital modulation, means digital we need to do in digital domain, and then we can directly do the multiplication with the carrier. So, and another point I just want to add, there are some advanced modulation scheme people are targeting for terahertz communication, where they try to bring the analog QAM also at this analog QAM also to reduce the effect. Let us say in high frequency communication we use the ADC. So, what we use a ADC or DAC, digital to analog converter we will use to convert digital to analog signal. But if your data rate is also is too high, and if you do not have the sufficient high DAC is available, then it is better to do this QAM also at analog, and it will help you to get the high efficient QAM. So, this is just you can come across various publication in nowadays where what they are talking about the QAM, analog QAM. So, you can apply same thing to the digital also, and this type of modulation requires highly linear power amplifier. It is very efficient, this kind of QAM modulation scheme is efficient. It can club the bunch of data in very less bandwidth, but it is a important requirement is a linear power amplifier, because you are changing amplitude as well phase, and if you want to try to reconstruct the signal QAM signal, then you need to have a better linear power amplifier. So, there is always a trade off that we have already seen in the first slide when we are discussing that power amplifier, linear power amplifier requirement with the modulation scheme. So, if we conclude the QAM, the concept of QAM can be extended to even a denser constellation. So, we have just seen an example of 16 QAM. So, there are many other 64 QAM or 256 QAM. So, denser QAM can be made, and you can achieve a much high data rate with lower bandwidth. So, if 8 for this example for 64 QAM, if 8 consecutive bits in a binary baseband stream are grouped, and then each quadrature component of the carrier is allowed to have 8 possible amplitude. So, one is a 8 bit with 8 possible amplitude, you will get a 64 QAM. The way we have done example for 16, you can apply for 64, 256 or any other higher dense QAM. There are several applications of employing QAM to save bandwidth. For example, in current 802.11.ga, we are using 64 QAM, which is able to achieve the data rate of 54 Mbps. So, this is what how the QAM is useful, and how we can use a QAM modulation for getting the highest data rate in the limited bandwidth. And it has a multiple application in various standards. People are using this modulation scheme, and this is just a basic idea of QAM. You can go through deep in the communication theory to study, or digital communication, you can study about the QAM modulation. So, I will try to conclude here for this lecture. We have seen the EVM, which is an important phenomena, QPSK and QAM. So, these three are important terms as far as this lecture is concerned. Thank you.